session of the morning. And first up, we have Dirk Husmeier of the University of Glasgow, who's going to be speaking about inference, emulation, and uncertainty quantification in cardiac mechanics.
Okay, thank you very much for the introduction. So this work is related to cardiac mechanics. That is joint work with various colleagues, most notably Hao Gao, who is in the audience, and he has a poster related to a very similar subject with some further details. The work has been carried out at SofTMech, which is in Glasgow, center funded by EPSRC. So we're well aware that cardiovascular diseases are a major health challenge, on average we have 460 deaths each day. And if you sort of look at the scar tissue of a heart, supposed to be after myocardial infarction, it would help clinicians enormously to understand the changed material properties of the scar tissue, but they obviously can't measure anything in vivo. Typically, they take magnetic resonance image scans. Here's sort of a scan of the heart, and that is not a static image, it's a dynamic image. This is the pump cycle. And really, a biomechanical, cardiomechanic model relates now the movement that they can see in the magnetic resonance image scans to material parameters. And that is what you want to exploit to then infer the parameters non-invasively for magnetic resonance image scans. So we start with the segmentation of the magnetic resonance image scans. So we extract the left ventricle of the heart, which we will be focusing on at a particular time point, at early diastole. I'm not going to talk any more about that. Then we use a mechanic model to then focus on the passive filling process, the inflation of the left ventricle during diastole. I don't want to talk about the cardiomechanic model either, so you'll find further details in that paper. And you can then solve the cardiomechanic equations numerically, the finite element discretization. The cardiomechanic model depends on material parameters. They are of clinical interest, but I'm not going into any further details about these parameters. I've told you 3 times what I'm not going to talk about for lack of time. So what I'm going to talk about, well, I want to focus on how do we infer these parameters? How do we learn them from data? In principle, you can measure them. You pump blood into the left ventricle, which with an ex vivo left ventricle. Then you measure the stress as a function of the stretch. And that's really what these cardiomechanic parameters really define. You can look at the stress-stretch relation in different directions. And then the parameters are related to the elasticity and the deviation from linear elasticity along the different directions. So that's an intuitive understanding of what the parameters give you, but you can't measure that in vivo. So we want to use magnetic resonance image data. So at the center point of our whole modeling approach is the cardiomechanic model. We extract the left ventricle at early diastole from magnetic resonance images. And we have the pressure at time point T1, early diastole. And the model depends on the constitutive material parameters that we're interested in. We solve the model numerically with finite element discretization to then predict the shape of the left ventricle at a later time point, at late diastole. We get the left ventricle, as mentioned before, from the magnetic resonance images. And we're interested in the constitutive parameters. And in principle, we can get them now by comparing the prediction from the model with the left ventricle at late diastole extracted from the magnetic resonance images. Then we can find the parameters that minimize the mismatch. Practical problem is computational costs are high for every numerical simulation. And so then if you do that the simulator, then you typically have computational times of about a week, and that is not feasible in the clinic. For that reason, we use an emulator. So we built a statistical surrogate model to mimic, emulate the original mathematical model. Okay, that is sort of a brief overview of the framework of mechanics, and so what I want to cover in my talk is, so how do we quantify the mismatch between the prediction from the model and then the patterns we extract from the magnetic resonance images? And we've tried 3 different approaches. The first approach is based on circumferential strains and the volume of the left ventricle at the end of diastole. So you can think of landmark points on the epicardial wall and how they move as a consequence of the inflation of the left ventricle during diastole, and that displacement that is our strain. And you can do that in different directions, and we focus on the circumferential directions, the circumferential strains, because they are particularly easy to extract automatically from the magnetic resonance image scans. And we also have the volume of the left ventricle at late diastole. So what we have now to match is the patterns from the magnetic resonance images. So that's a 25-dimensional vector, the volume of the left ventricle at late diastole, and 24 circumferential strains. Then the prediction from our model. That prediction depends on the geometry of the left ventricle at early diastole, and then the parameters, the cardiomechanic parameters that we are interested in inferring. So you could try to minimize the mismatch. That gives you a point estimate without any quantification of uncertainty. To quantify uncertainty, we want to get the whole log likelihood. So here you see the log likelihood under a very simple additive Gaussian noise model. You can generalize that straightforwardly to allow for correlations between the residuals as well. Once you've got the likelihood, that opens the door then to Bayesian inference. But you can't use the original model. We will have to build the emulator. The emulator needs to have information about the shape of the geometry of the left ventricle at early diastole. And here we use a dimension reduction in order to have a dimension on which we can actually build the emulator. So we put the left ventricle geometry to a PC dimension direction, typically map onto the first 5 to 10 principal components. Then we build a Gaussian emulator. Then we run hybrid Monte Carlo simulations to now sample the parameters from the posterior distribution. Now you've got the parameters, and remember the stress curve. So if you have fixed parameters, you get a fixed stress stretch curve from your model for fixed parameters. We sample parameters from the posterior distribution that gives us a distribution of stress curves that can be represented here. This shaded area shows you the posterior 95% credible interval. You see the posterior mean, and you also see the true stress curve. You see that is within this 95% credible interval. That is along two different directions, along the myocytes and along the sheet direction. That is for a particular geometry from a healthy volunteer. And here's another example from another healthy volunteer. So that is good news. The bad news is, here's a parameter that we cannot really properly infer. We see the posterior distribution of the quadratic difference from the ground truth value. So the best value would be to have a delta spike sitting at 0. We have a larger value that indicates that we have log have accuracy, poor estimation, and also the uncertainty is quite high. That is repeated for 6 geometry from 3 different healthy volunteers. And that's not too surprising because the circumferential strains don't have any information about the elasticity in the perpendicular direction. So they're not sufficiently informative to give you all the parameters. So that's the idea then is, because we do Bayesian analysis anyway, to use prior knowledge from the literature, and we want to use the clots prior. Gernot had already alluded to that in his talk. So that's a study where the authors looked at the depressed blood into the left ventricle of an ex vivo heart, and they measured then the volume change. And then they look at the normalized volume, which you see at the bottom right. That is the volume at the reference pressure P minus the volume of the unloaded state divided by volume at pressure 30 millimeter mercury minus the unloaded state. And you see, sort of, the authors found a nice empirical relationship represented by this clots curve in exponential law. So we want to integrate that into our Bayesian framework. The first thing is it's a bit odd the way they present it, because the independent variable is really the pressure. The volume is the dependent variable. So we show that differently. So in the more conventional form, that now the independent value is the horizontal axis that turns the exponential form into a log form. We want to allow for heteroscedasticity that we see in the data from their paper. And so the model basically looks at a model defined by the clots curve that comes from their empirical law, having 2 parameters. These were the 2 parameters of the exponential curve. And we have a variance that is a low-order polynomial of the pressure. And then we can use that, interestingly, by getting back to the original volume at the reference pressure 30 millimeter mercury, just a simple remodification. That means our model can now predict the volume at 30 millimeter mercury. The input that you need is the volume at your reference pressure at late diastole. Now, our cardiomechanic model is fitted to the volume at late diastole, the circumferential strains at late diastole, with the dependence on the parameters, and standard sigma is of the standard deviation of our noise model. And then that model also predicts the volume at 30 millimeter mercury. And these volumes should match. We do Bayesian inference. You have the whole uncertainty, the posterior distribution of these volumes. And if they're in agreement, then we have a good parameter estimate according to the prior assumption that we should be consistent with the clots curve. So we quantify the difference with a product of expert approach, and so see if the distributions overlap, then that value is high. The nice thing about it is that under Gaussian distribution that has a closed form solution, and then we get the posterior distribution just by normalization. All right, so what does the prior distribution look like? For two parameters, where the horizontal axis is the parameter that is well informed by the circumferential strains, and the vertical axis is the parameter that is weakly identifiable based on the circumferential strains. You see that now as a consequence of using the data, the circumferential strains to fix parameter theta 2, you reduce the uncertainty of parameter 33. That's parameter theta 3, that is the weakly identifiable parameter. And you see that as a consequence of that, first the accuracy improves, so the posterior distributions get closer to 0. That's posterior distribution of the quadratic difference from the ground truth value. And you also see that the uncertainty has reduced compared to just the uniform parameter. Okay, so that's joint work with Lazarus and Hao Gao. And so that was our sort of first focus on circumferential strains. In some sense, in order to make up for the weakness or lack of information, we used then prior from ex vivo data using the clots curve prior. But ex vivo data, then the question is how representative is the ex vivo tissue for in vivo organ? So we tried a different approach, only looking at the volume of the left ventricle. So we focus on diastole and the inflation of the left ventricle during diastole. And we only extract the volume as a time series going from early diastole to late diastole. And the reason for that is that the volume can easily be extracted from the magnetic resonance image scans. So that is work of former postdocs of ours, Arash Rabbani, who is now a lecturer at the University of Leeds. So his idea was take the magnetic resonance image scan, and then apply a sort of a neural network, a unit for segmentation. So you identify the right ventricle, the background, left ventricle wall, and then the inner cavity. Then you look at the cross-sectional area for different times and different distances from base. All these green circles are cross-sectional areas. We smooth the whole process with a Gaussian process using a periodic kernel, and then we can get the volume at a specified time point by numerical integration. That gives you now a time series of volumes. And if we now compare the volume that we've automatically extracted from the cardiac magnetic resonance images and compare that now with segmentation, manual segmentation by an expert, you see a good agreement, and the root mean square error is in the order of 6.7. If you give the task to two different experts, you get a root mean square error in the order of 5. So that is pretty close to the intrinsic uncertainty that we have anyway. So having got that far, then we want to actually use now inference, and a PhD student of ours, Yuzhang, was looking at that. So he wanted to build an emulator, Gaussian process emulator. We have now the combined space of the parameters and the time points, and then we use a check from spatial statistics. So we model the covariance matrix as the Kronecker product of a covariance matrix only in the space of parameters, and a covariance matrix only in the space of time points. And then the inverse of the covariance matrix is then the canonical product of the two inverse matrices. That brings down the computational complexity quite substantially. That sort of enables building then this emulator in this increased output space. We looked at real data, left ventricular volume time series from various healthy volunteers and patients. We obtained the posterior samples of the parameters. Now we don't have a gold standard here. We put the parameters back into the model, then simulated left ventricular volumes, compared that with the data, and found that is in good agreement. So that is good news. And we also looked at a particular parameter, looked at the posterior distribution based only on the end diastolic volume, that's shown as a dashed line, and the whole time series of volumes, that is a solid line. You see improved accuracy and also reduced uncertainty. That is also good news, but there is a fly in the ointment, and that is not representative for all the parameters, because if you then, when we're looking at the parameters more globally, we did not necessarily see that always consistently coming out so positive. Here you see 4 parameters. These are the 4 parameters of the cardiac mechanic model, of the Holz-Apfel-Ogden model. And we covered the parameter space with a space filling design. These are the different rows. And these are 4 parameters. And you find here the situation which is pretty good. That's what we expected. Reduction of the uncertainty, improved accuracy, but it's not always the case. In order to understand why that's not always the case, we then looked at some sort of sensitivity analysis where we cover now the parameter space, where we keep 2 parameters fixed and plot now the difference of the volume from mid-diastole to late diastole and see how that responds to variation of the parameters. And for visualization, we can only look at 2 parameters, keeping the other 2 parameters fixed. You see here is a parameter configuration where a small change of parameters actually leads to a large response, so our volumes are informative, and that leads to a substantial reduction of the posterior uncertainty. That's what we were hoping for. And then we also have areas which are sort of more or less on a plateau, so a perturbation of the parameters doesn't really lead to a large perturbation of the or change of the volume, and that is then reconfirmed by the simulations. The posterior distributions do not really shrink, they are as uncertain as before. So the good news in some sense is that well, the volumes can be easily extracted. That would be able to be put into the clinic, and we can get an emulator with reduced complexity using standard tricks from spatial sample statistics. But then the practical identifiability is not always as good as we had hoped. So then we try the full exploration of the displacement field. So far, we've always looked at reductions, either using the circumferential strains or a time series of 10 volumes. Can we use the full 10, the displacement field? We model the left ventricle by a mesh of typically in the order of 17,000 nodes. Can we look at the full displacement field? And building an emulator here, the lossy process emulator, would not be feasible if we use a graph neural network. So we represent the left ventricle by a mesh. We have nodes, we have edges, we have dependence on the parameters that we're interested in, and we also bring in information about the shape, the volume of the left ventricle at early diastole via a dimension reduction via principal components. And so running a simulator for inference is computationally too expensive. So we map now the nodes in the original physical space with a neural network in a high-dimensional embedding space. And then we use message passing on this graph in this embedding space. We update the states of this graph, and then we map that back with a neural network back into the physical space. And then we can iterate that a few times. So that initially didn't work. The reason is that it takes too long to move from one part of the graph to the other. We introduce shortcut connections. That's what we see here. We've got different, more coarse-grained layers in parallel, where we can get shortcuts, like being on a fast lane where information can travel faster from one part of the graph to the other. And then we train the graph by sort of running simulations, covering the parameter space with a space-filling design. We look at the prediction from the simulator. Then we train the parameters of the graph neural network so that we minimize the mismatch between the prediction from the simulator and from our emulator. And then we found that first the number of message passing steps is not so critical as a consequence of the shortcut connection. And also the embedding dimension isn't so critical as long as the embedding space dimension is sufficiently large. So the graph neural network, then we can use an extra trick by making it physics informed. So if you have a small ball on sort of a hemispherical glass ball and you let it release it from the current position, that it will come to rest somewhere, and you don't need to know the exact trajectory. You know that it will come to rest at the minimum of the potential energy. And for the left ventricle, it's sort of similar, that we know that finally it will come to rest at late diastole at the minimal potential energy. So rather than actually running now over simulations, which we did for the previous approach, we run simulations with the simulator and then match the graph neural network against these simulations, well, all we're doing now is to cover the parameter space with the space-filling design and then minimize the potential energy. But we don't need to run any extra simulations anymore. So we do a lot away with these simulations altogether and bring more physics into the whole graph neural network representation. So to finish, I think I'm close to the end of my time slot. Here's the left ventricle configuration at early diastole. If you run the simulator based on finite element discretization, you see how that now reconfigures. The left ventricle inflates. You see the legend, the colors indicate the amount of displacement of strain. That is what you get with the element discretization using the original simulations. That is with what you get with the physics-informed graph neural network. So just by eyeballing these two graphs, they look pretty similar. If you look at the mismatch between both, then that looks pretty good. On the left, you see the absolute mismatch. In terms of the relative mismatch, we never get a mismatch of more than 0.5%. And we bring down the computational complexity from running full simulations with abacus in the order of 10 to 15 minutes down to well, less than 10 to the minus 3 seconds on using after training the graph neural network. That's a reduction by 5 orders of magnitude. Okay, the lesson we've learned here is that you can build an efficient, accurate emulator. We haven't investigated inference yet, and the disadvantage in terms of clinical impact, obviously, is that getting the full displacement field is less straightforward. So for that reason, we were hoping to get more out of the time series or volumes, and that is still something that we are pursuing by bringing in cloth curve prior information. Okay, so I'm a minute over my time slot, so let me finish here. The work has been funded by EPSRC. It's a sort of SofTMech center in Glasgow, and just as a final announcement, if anything of that is of interest to you, we still have a bit of money on the partnership resource funding budget. So if you have an idea how you can do things differently and possibly better with a different approach that is complementary to our approach, so we can fund 3 projects, sort of short-term proof of concept studies for postdoc to be employed for 2 or 3 months. So just send me an email. So the formal process is write a short 2-page outline proposal that goes formally to our management team, and then sort of raise on a light touch review. Then we can still decide on funding extra 3 projects that are aligned with our research, which focuses on the cardiac mechanics of the passive filling process in diastole. Now 2 minutes over the time, I should shut up. Thank you.
There's one quick question. We'll take that one.
Thank you very much for the presentation. And regarding the calculating the cross sections, you mentioned that you obtained those from the 2D slices from the scans.
Yes.
And for each slice, you can get 1 cross sections. But usually for 2D, I mean, at some point you would not have an image that is perpendicular to the center line of that object, which is there a 2D cross section. How did you overcome that? Because if you just get cross section from 2D slice, it might be not perpendicular to that. So, and the result might be not very accurate. I don't know.
Yes, we do the numerical integration of the different slices that gives us the volume. And then it goes into a neural network to match that. Again, that is input to a neural network. That neural network gets also the volume from an expert. So it gets the information from first the segmentation, then the numerical integration with the Gaussian process, and the final correction is based on another neural network that takes that as an input, gets another output from an expert, and can do then the final nonlinear correction.
Thank you, and let's thank the speaker again.